Hello, everyone. Um, this is the lecture that was supposed to be given on Thursday, March 18th. So I'm recording it now, and I hope you get a chance to watch it before the next week lecture on Tuesday. Um, so last lecture was about areas. The main theme is applications of integration, the geometric applications. I talked about areas in the plane, and I also talked about volumes, how to find volumes of solids, and I'm gonna quickly review what we talked about last time as far as volumes go, and then we'll see more related ideas and we'll see many more examples. So the basic um, fact that we developed last time was whenever you have a solid in the space, sorry about that. Whenever you have a solid in the space, think of it as a potato, something. You can find its volume by integrating the so-called cross-sectional area. Namely, if you place this solid next to some axis, which I'm supposed, which I suppose is to be the x-axis, and the solid extends from A to B. If I cut this solid at some x, and I look at the cross-section, the area of this cross-section, which depends on x, is the so-called cross-sectional area function. That's A of x. So A of x is the area of the cross-section of the solid when you cut it above x. Here, x could be anything between A and B. So once you have this cross-sectional area function, the volume can be recovered by integrating that cross-sectional area function from A to B. That's a general principle. And I showed you some examples using this general formula. But there are some special cases in which when we apply this formula, the, the appearance of the formula will change. And one special category of solids that we discussed was solids of revolution. So I want you to realize that this is the sort of the most general case that applies to any solid. This formula applies to any solid, whether it's a solid of revolution or not. But in the very special case that your solid is obtained by revolving a region around some axis, then this general formula takes a special form. And that's what we also discussed last time. So uh, the basic case is, as you recall, is somebody gives me the graph of a function f. I'm assuming this graph is, so the function is positive, so the graph is above the x-axis. I look at the region under the graph of f between x equals a and x equals b, namely this region. So this is a region sitting in the xy plane. And then I ask myself, what happens if I rotate this region around the x-axis? If I rotate the region around the x-axis, I get a solid whose cross-sections are round disks, simply because this solid is obtained by revolving. This is an example of a solid of revolution. So the basic case is we take the region under the graph of some function f and we rotate it around the x-axis. In other words, this region is bounded between the graph of f of x, the x-axis, which has the formula y equals 0, between two vertical lines x equals a and x equals b. So that's the type of region we consider. One side of the region is leaning against the axis of rotation. And when you rotate it, you get some object like this. And in order to compute the volume, all I have to do is to figure out the area of a typical cross-section made above some point x. If I cut this solid of revolution at some x, what I see is, so this is another view of the cross section. This is the perspective view, which looks like an ellipse, but really what it is a round circle whose radius is f of x, because if this cut is made above x, the radius is this height, but this height, look where it comes from. This height is like this height here, right above x, so it's the y-coordinate of this point, which is f of x. So this cross-section is a disk of radius f of x. The cross-section at x is a round disk of radius f of x, and therefore it has area. What is the area of a disk of radius f of x? It's pi radius squared, so it's pi times f of x squared. That would be the area of this cross section. So my a of x in this special case will be pi f of x squared. And therefore, using the general principle that the volume is the integral of the cross-sectional area function, I get the formula that the volume of this solid of revolution is the integral from a to b of a of x dx, but a of x is this. So pi is a constant. I can pull it outside. So it's going to be pi times integral from a to b of the square of my function that I started with. So all you have to do is to take this function, square it, and then integrate it from a to b, and then multiply your answer by pi. This method is called the disk method simply because such solid of revolution, when you look at the cross-section at each point, it's a disk. So the word disk here refers to the shape of the cross-section. And I showed you a couple of examples of this method last time at the end of the previous lecture. So I hope you've had a chance to watch it. But I'm going to show you many more examples today, so no worries. But before that, I want to, in some sense, we're going to get a lot of mileage out of this general formula by applying it to special cases. One special case was this, so we ended up with this formula, which is referring to this situation. Now, another variation is, what if I have, so let me also talk about this, and then I'll show you many examples. What if my region is not bounded between the graph of f and the x-axis? What if my region is bounded between two graphs? Say the upper graph is f and the lower graph is g. What if I take such a region and then rotate it around the x-axis to get such a solid? Down here is an attempt to visualize what happens when you take this region and rotate it around this line. You get a solid which now has a cavity inside. As you can see, there is a hole inside now because of this area. So your region has some distance to the axis of rotation. When you rotate it, it's not leaning against the x-axis, so you get some cavity in the middle. Now, I can apply the same idea to this case. All I have to do is to look at the cross-section. So I pick some generic x. I cut this solid vertically. And this time, what I see is not a disk, but is a ring, something like a washer. And that's why this method is called method of washers, or washer method. So when I look at the cross-section, I see a disk with another disk removed. So I see the region between two disks. The larger area, I'm sorry, the larger radius, this radius comes from f. So the radius of the bigger circle is f of x. And the smaller radius comes from the graph of g. So the smaller radius here is g of x. So I'm looking at a washer whose outer radius is f and the inner radius is g. That would be the shape of my cross-section at x. And what is the area of this region? It's the area of the big disk minus the area of the small disk. So it's pi f of x squared minus pi g of x squared, the difference between the areas of the two disks. And therefore, the general principle that the volume is the integral of the cross-sectional area in this case reads, volume is the integral of this function. Of course, I can factor the pi, and since it's a constant, I can put it outside. So the formula reads, volume is equal to pi integral from a to b of f squared minus g squared dx. So I have to take the upper function, square it, and then subtract from it the square of the lower function, and then integrate that and multiply the answer by pi. So the previous case, which was the disk method, is a very special case of the washer method in which the second function g is the constant function 0. So its graph is just the line y equals 0, in other words, the x-axis. So if in this formula you assume g of x is 0, your region would look something like this. And in this formula, g will be gone, so you recover the formula for the disk method. And in this case, your washer reduces to a disk because the inner radius will be 0. So as you see, we're not really talking about new things. We are just looking at variations of the same theme. So once you know the general formula that the volume is the integral of a of x dx, the integral of the cross-sectional area function, you can apply it in a variety of situations. We're just applying the same idea over and over again in different situations. Okay, so let's take a look at a bunch of examples. When we do specific problems, we gain experience and we learn more about what's going on. One thing that might make some of you nervous when it comes to these problems is you may think that you must have good drawing and sketching abilities, and this has something to do with your artistic skills. Maybe you don't feel comfortable drawing three-dimensional pictures. That's not the issue. You don't have to. This is not about your drawing skills. You can just look at the region in the plane and look at the axis of the rotation and just imagine. You don't have to draw anything. Just imagine what would happen. And since we already have the formulas, essentially it boils down to plugging in the correct stuff into the formulas that we already have. Okay, so I'm going to show you a bunch of examples. Find the volume of the solid obtained by rotating the given region bounded by the given curves about the given axis. So in each case, I give you a region and I give you an axis. And the question is, what happens if I take that region and rotate it around that axis? The solid that I end up with is a solid of revolution. What is the volume of it? Okay, the first example is the region is bounded by these curves, y equals 1 minus x squared, which is this upside-down parabola. And the second one is y equals 0, namely the x-axis. So the region bounded by this upside-down parabola and the x-axis is just this blue region. So that's my region, bounded from above by 1 minus x squared, from below by 0. And I'm going to rotate it around the x-axis. So this is precisely the situation for the disk method. Remember, for the disk method, we have some function f and the x-axis. So the upper function is something like f. The lower function g is 0. And we are rotating it around the x-axis. When I do that, just to imagine what happens when I take this blue region and rotate it around the x-axis, I will end up with a solid that looks like this. Something like, I don't know, an onion, something like a, pretty much like a football, not a round thing, but it's kind of pointy here and here, but it's something like that. So we want to find the volume of this thing. Well, all I have to do is to apply the formula. Integral from a to b, integral from a to b of f of x, which is this, squared, and then I multiply my answer by pi. The only thing is that I have to figure out the bounds of the integral, my a and b. And for that, I have to find the intersection point of these two. In other words, I have to figure out where this function has 0. But that's a simple thing. Set 1 minus x squared equal to 0. And you can easily see that x will be plus minus 1. So it's very easy to see that this point right here is -1, and this point is +1. That you can clearly see. But the way you find them is by, as usual, is by setting this equal to this and then solving for x. So the volume will be pi, integral from -1 to 1 of my f of x, which is 1 minus x squared dx. Right? So this is pi, integral from -1 to 1. Let's square this. You get 1 minus 2x squared plus x to the 4th dx. So I take this expression and I square it. So it's 1 squared, which is 1, minus twice first times second, which is this term, plus the second one squared, which is x to the 4th. And this is an elementary integral. So keep the pi. Antiderivative is x minus 2/3 x cubed plus 1/5 of x to the 5, evaluated at, let me get this out of the way, evaluated at 1, -1. You could also, since this function is even, when you integrate an even function over a symmetric interval such as -1 to 1, it suffices to integrate it from 0 to 1 and then double the answer. You could do that too. But anyway, this is a very simple computation. So you plug in 1 and then -1 and then subtract. And what you get is 16 pi over 50. So that's the exact value for the volume of that solid. You see, you didn't have to draw any picture. Oh, I apologize. For some reason, I don't know what's wrong with my mirroring app. And I have no idea how long this was disconnected, but I hope you can see and reconstruct everything here. Let me quickly, in case you didn't have the image when I was explaining it. This was the region bounded between this parabola, 1 minus x squared, and the x-axis. And I rotated it around the x-axis. So the volume is obtained by the formula pi times integral from a to b of f of x squared. This is the disk method. This is the first case we considered. So I squared this function. I get this degree 4 polynomial whose integral is very easy. Antiderivative is x minus 2/3 x cubed plus 1/5 x to the 5. Integrate, evaluate at the upper limit 1 and then lower limit -1, and then subtract and then multiply by pi. If you do that, you get this answer, 16 pi over 50. Okay? So this is the simplest case of computing a solid of revolution. This is the simplest case. Let's take a look at another example. Now, the region that I have is bounded by y equals x cubed, which is this curve, part of this curve. The whole graph of x cubed looks something like this. Imagine. And then the second one is x. So that's the straight line. So when I take this x cubed and this x, there are two regions bounded by them. But it's telling me that I have to focus only on the part where x is positive, so I just end up with this region. Bounded from above by x, from below by the graph of x cubed. And I'm going to take this region, and I'm going to rotate it around the x-axis. So you can imagine that if you take this region and rotate it around the x-axis, you get something like this. So it's going to be something like a, I don't know, some kind of a cup or ball. From outside, it looks, so it's going to be something like this. If I hold it in my hand, let me draw it. If I hold it in my hand, from outside, it looks straight, like a cone, like a martini glass, but the inside is curved. So that's the shape of the solid that you get. You can imagine. But again, you do not need to be able to draw this in order to compute its volume, because once you realize that you have a region, that's the important thing. Once you realize that you have a region bounded above by some graph, bounded below by another graph, between two values a and b, and you're rotating it around the x-axis, you know what to do. This is the washer method. So this would be an example of this case that I was talking about. The region is bounded above by some f, bounded below by some g, between two values x equals a and x equals b. You rotate it around the x-axis. So you get that case. Again, the only thing I have to do before applying the formula is to figure out the x coordinates of these endpoints. So what are these x coordinates? It's pretty obvious that this is 0. Again, I have to set them equal. I have to set x equal to x cubed and solve for x. So that's x cubed minus x equals 0. So if you factor in x squared minus 1 is equal to 0. So either x is 0, or x is 1, or x is -1. -1 is the other point of intersection over here, which is irrelevant. So the only relevant values are 0 and 1. So I already know that this thing right here is x equals 1. Okay? So again, this is very simple. You can figure it out, or you can just guess, because what is that x value which is equal to x cubed? I mean, that's 1. All right. So according to the formula that we had, the volume, this is the washer method. It's pi, integral from 0 to 1. Those are the values of a and b. The upper function squared, I have to square the upper function, which is x, minus the lower function squared. When I square x cubed, I get x to the 6th dx. So I set up the integral using the general formula that I had. Again, this is like f of x squared, and this is like g of x squared. I'm applying the general formula in this special case. And again, fortunately, this is a very simple integral, so I don't have to worry about how to compute this integral. Antiderivative is 1/3 x cubed minus 1/7 x to the 7, evaluated at 1, then 0. So this is pi. When you plug in 1, you get 1/3 minus 1/7. When you plug in 0, you get nothing. So that's 4. So this difference is 4/21. And therefore, you get 4 pi over 21. And that's the exact value of the volume. Again, whether you're doing this on paper or in WebAssign or during a test, I recommend that you always keep your answer like this. It would not be a good idea to take the decimal approximation for pi, for example, replaced 3.14 blah, 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 something, and then multiply it by 4 divided by 21 and write the answer as an approximate decimal. Don't do that, because that would not be the accurate answer. So always when your answer involves pi or e, these universal constants in math, you better keep them as such, except in like applications and engineering problems or in some specific applications, you want to know the rough approximation. So you just use your calculator to get an idea how big that number might be. But when you do math, you tend to keep your answers this way. Okay. Now, I want to tweak this problem ever so slightly. And that's going to be our next problem. So keep in mind that this was the region bounded from above by x, from below by x cubed. So this shaded region in blue. And the axis of rotation was the x-axis. Now, in my next example, I want you to do this. Take the same region. So I'm not changing the region. Again, the region bounded from above by x, from below by x cubed. But I don't want you to rotate it around the x-axis. I want you to rotate it around this line, which is the line y equals -1. The x-axis is the line y equals 0. This time, I want you to rotate around the line y equals -1, which is further down. So it stays farther than the x-axis relative to that region. So if you want to just imagine what this difference would be, let me sketch. It's very hard to sketch these things on a slippery screen. I wish we could do it on a chalkboard. So in the first case, when you rotate around the x-axis, the kind of region that you get looks like this. Something like this. But this time, when you take the same region and rotate it around this axis, which is further down, what you get is something like this. So it's a much wider solid, and it has a cavity inside. So this is like there is a hole here, but in this case, there is no hole. So in this case, there is no hole. In this case, there is a hole. So I hope you can realize the difference between the two cases. It's not going to be the same shape. So one of them looks like, if I just rotate it so that it's standing, one of them looks like this from outside, the other one looks like this from outside. And this one has a hole in it. This one doesn't. So that's the difference between the two cases. When you move the axis of rotation, of course, you don't expect to get the same thing, even though it's the same region. All right, so no big deal. I want you to imagine something. When you do the cylindrical shell, the washer method. Remember, it all boils down to, let me go back to that slide. When you do the cylindrical shell method, basically, I'm sorry, I don't know why I keep saying cylindrical shell. When you do the washer method, basically what you have to do is you have to look at the cross section. In this case, it's a ring or washer, and look at the outer radius and look at the inner radius, and then using that you can find the area of the cross section, and then you use the general formula. So in this case, since the axis of rotation is the x-axis, the outer radius is f of x, and the inner radius is g of x. Now look at this picture. If my axis of rotation is the x-axis, like in the previous problem, when I pick some x, the outer radius is x, and the inner radius is x cubed. That's what we did in the previous example. The outer radius was x, the inner radius was x cubed. Now in this case, the axis of rotation is this line, the line y equals -1. So when I pick some x and look at the cross section, I have to figure out, so this is the axis of rotation. So this is going to be the center of that ring. I have to figure out the outer radius, which is now this length, and the inner radius is now this length. So what are those? If you pick some x, if you look at the distance between these graphs and the line on the axis of rotation, this distance is just x plus this extra distance, which is 1. This extra distance is 1. So when you move your axis of rotation to this line, y equals -1, your outer radius of the section of that washer will be x plus 1. You have to add 1 to it. And your inner radius has to be x cubed plus 1. So you have to add 1 to both radii. So cross section at x is a washer whose outer radius is x, and then I have to add plus 1. Where does this plus 1 come from? It's this extra length, whose and inner radius is x cubed plus 1. And therefore, A of x, which is the area of that washer, would be pi x plus 1 squared minus pi x cubed plus 1 squared. Previously, when the axis of rotation was just the line y equals 0 or the x-axis, I didn't have this plus 1 and this plus 1. And this formula was pi x squared minus pi x cubed squared, which is x to the 6th. But now, both radii, I have to add 1 to them. I have to add 1 to this function. I have to add 1 to this function, and then proceed as before. Again, why do I have to add 1 and not any other number? That 1 is this distance. So if the axis of rotation, for example, was around the line y equals -5, I would have to add 5 to both these functions. And then square them, take the difference, integrate, and then multiply by pi. So maybe I need some extra paper. So that means the volume is pi integral from 0 to 1. Remember, the bounds won't change. The bounds of integral are still 0 and 1. The only thing that changes is I've added that extra distance 1 to both functions. So it's going to be x plus 1 squared minus x cubed plus 1 squared. I take the difference and I integrate. So this is a simple integral. I mean, it's a little tedious, but it's nothing complicated because it's just the difference between two low-degree polynomials. So let me square both of those. X plus 1 squared, if I expand it, it's going to be x squared plus 2x plus 1. And x cubed plus 1, when I square it, it's going to be x to the 6th plus 2x cubed plus 1. I take the difference and I integrate. So that's pi integral from 0 to 1. Let's clean up a little bit. I have x squared plus 2x. This 1 and this -1, they cancel out. Minus x to the 6th minus 2x cubed dx. And this is pi. Antiderivatives are 1/3 x cubed plus x squared minus 1/7 x to the 7th minus 1/2 x to the 4th, evaluated at 1, then 0. Yep. So when you plug in 1, you get 1/3 plus 1 minus 1/7 minus 1/2. And when you plug in 0, you get nothing. You do this, and you simplify this fraction. I think I have this number. I computed this number before, and the answer is 29 pi over 42. Okay. So one more time, the new feature or the novel feature of this example was that I was given this region, and instead of the usual axis of rotation, which is the x-axis, I moved the axis of rotation further down to the line y equals -1 at distance 1 from the previous case. And I just told you that the effect of this is adding 1 to both functions before you um, apply the formula. That's clear because, one more time, if I cut this thing at some x, this distance is x. Now I have to add 1 to it, and that's going to be my outer radius. From here to here, that's going to be my outer radius, which is what it used to be, namely x plus this extra 1. So that's why the outer radius is x plus 1. And look at the inner radius. The inner radius is this much, which is x cubed, plus an extra 1. So from here to here, you get x cubed plus this additional 1 unit. So that's why the inner radius is x cubed plus 1. There is another way you can justify this addition of 1. Maybe for some people this is easier. So pay attention, please. I just want to say something that probably will make it easier for some of you. If I imagine, just imagine that this was your x-axis. So imagine that this was the usual x-axis, and you were rotating this region around your x-axis. Then the formula would be upper function squared minus lower function squared, integral of that, then times pi. But if this is my x-axis, what would be the new formula for this function? You have to shift x 1 unit up. So it's going to be x plus 1. And if I pretend this to be my x-axis, what's going to be the formula for this curve? It's not going to be x cubed. It's going to be x cubed plus 1 because you're shifting x cubed by 1 unit. Either way, the new functions that should go into the formula for the volume are the old functions when you add 1, this extra distance to it. Okay? So I'll leave it to you to think about this, whether you like the first method by looking at what the new radii are, measure the distances from the axis of rotation up to your curve, and you see that there is an extra 1 you have to add to each radius. Or the second point of view, think of this as your new x-axis and figure out the new formulas for these. So obviously, you have to shift everybody up by 1 unit. Either way, you end up with the same conclusion. Let me do one more example. Excuse me. Now I'm looking at this almond-shaped region, this I region, bounded between y equals x squared, which is this parabola, part of the big parabola, of course, and y equals square root x, part of this curve. So in other words, if I were to graph this thing on my scrap paper, I would see a parabola, y equals x squared, and I would see something like this, which is y equals square root of x, and the region bounded by them is this area. Okay, so that's what I have right here. I sort of deleted the extra stuff. I just kept the region. So this is a region bounded from above by this guy, the graph of f, bounded from below by this guy, x squared. That would play the role of g. Axis of rotation is standard. It's just the x-axis. So this is a standard situation in which I can apply the washer method. All I have to do is to figure out the endpoints. So this endpoint is obviously 0. This endpoint is, again, 1. If you set these two equal, you can guess that it's 1 because square root of 1 is 1 and 1 squared is 1. But again, you set root x equals to x squared. Maybe square each side. X equals x to the fourth. Then x to the fourth minus x is 0. Then x times x cubed minus 1 is 0. So either x is 0 or x cubed is 1. The only number whose cube is 1 is 1. So no matter how you do it your favorite way. This is elementary algebra. You realize that the endpoints are 0 and 1. For some reason, it just happened that in most of these problems, our endpoints were 0 and 1. But that's, I mean, I don't want you to get the idea that it's going to be always 0 and 1. It's just an accident. All right, so I don't have to worry about any tweak in this picture. We have the standard formula. The volume is pi, integral from a to b, which is 0 to 1. Upper function squared, let me write it like this. So I have to square the upper function minus the lower function squared. Let me write it like this. And then I will simplify it. That's all there is to it. So that's like f of x squared minus g of x squared. So this is pi, integral from 0 to 1 of x minus x to the fourth dx, which is pi. Antiderivative is 1/2 x squared minus 1/5 x to the 5. Evaluated at 1, then 0. So this is pi. When you plug in 1, you get 1/2 minus 1/5. When you plug in 0, you get nothing. So this is 3/10. So the final answer is 3 pi over 10. This was a very simple problem. It's just mere substitution. We have the formula, we just plug in various things. Okay? So let's move on to the final example before we learn something new. So I'm going to talk about this case. And there is another slightly new feature in this example. Not really new, but anyway. This is what I have. The region is bounded between this curve, x equals y squared, and this curve, x equals y. So instead of the usual formula, y equals f of x, I have x equals f of y. X equals some function of y. And x equals some function of y for the other one. And instead of rotating around the x-axis, which has been the usual thing, I'm going to rotate around the y-axis. So I'm going to get something like this. So what should I do? Well, when you think about it, this is exactly like any of the previous cases. The only thing is that the role of x and y coordinates have been switched. What I mean by that is that this problem is totally identical to having this problem. Y equals 2x, y equals x squared, rotated around the x-axis, which is the standard washer method. These two problems are completely identical. The only difference is that the role of x and y are switched. So you can just make this observation and say, okay, this is just like a usual washer method problem. All I have to do is to take my upper function of y, square it, minus the lower function of y, square it, integrate it from y equals 0 to y equals whatever I have to figure out, and then multiply by pi. So let's figure out these coordinates, the endpoints. Obviously, this is 0. This endpoint is 0, y equals 0 here. And what about this endpoint? Where do you think this is? Well, I have to figure out the y coordinate there. So the way to find the y coordinate there is by setting this equal to that and solving for y. So if I set y squared equals 2y, in other words, y squared minus 2y equals 0, I can factor y. Y times y minus 2 is 0. So either y is 0 or y is 2. Already from the picture, we saw that one of the roots is y equals 0, and now we know that the other one is 2. Which makes sense, because let's check. When I take y equals 2 and put it here, my x will be 4. And when I take y equals 2 and put it here, my x will be also 4. So that is an intersection point. So if I set it up as an integral, the volume, again, I'm not doing anything new. This may seem like a new problem, but it is really one of the old problems in disguise, in the sense that it's exactly one of the old problems, but in this problem, what used to be x is now y, what used to be y is now x. So it's going to be pi integral from 0 to 2. Those are the bounds, the lower and upper bounds for y. Upper function squared, when you look at it correctly, this plays the role of your upper function, f, which is going to be 2y squared, minus the lower function. This plays the role of the lower function squared. And then you integrate this with respect to y. So this is just pi times integral from 0 to 2 of 4y squared minus y to the 4th dy. Y happens to be your variable of integration. That's fine. So that's 4/3 of y cubed minus 1/5 of y to the 5th, evaluated at 2, then 0. So when you plug in 2, let's see, so you have pi. When you take 2 and plug it in for y, you get 32 over 3 minus 2 to the 5th is 32, so it's 32 over 5. And when you plug in 0, the lower bound, of course, you get 0. So that doesn't contribute at all. So 1/3 minus 1/5 is what? 2 over 15. So this is going to be 2 times 32 is 64 pi over 15. And that is the exact value of the volume. So maybe I can put a comment here in case you review the stuff later, that just interchange X and Y and apply the washer method. That's the idea. That's the idea here. Okay? All right. So as you see, we started with only one basic principle, that the volume of any solid is the integral of its cross-sectional area function. And then we try to apply that general principle in a variety of situations. All of these so far have been solids of revolution, but you could rotate it around the x-axis, you could rotate it around another horizontal line, and by switching the role of x and y, you can treat the cases where you're rotating around the y-axis. Now, let me pause the recording here, and in the second part of the recording, I will show you another method, the so-called cylindrical shells method, which is slightly different in nature, but also very useful. So I'll see you soon.